So today we're going to go through the last lesson of Module 5, and this is the last lesson that we are going to have together. And in this lesson, we're going to be looking at our AC distribution systems. We've already looked at the introduction and we've already looked at the DC systems. So this one is purely on the AC. As we already showed you on lesson 1, when we talk about the alternating current, we have got a change in direction where your current is traveling, and it changes periodically as per what you are seeing at the bottom, and these pictures were also shown on your lesson 1, where you've got your AC current going in a sinusoidal wave system where it goes from 0 going all the way up and then going down again at 180 degrees back to 0. And so when we also look at the circuit diagram, you can see that from your source point that current can be going on either direction towards it. So to date, the entire electricity system is really done on AC, except for those very few exceptions that I shared with you under the DC distribution systems. So the generation, the transmission, as well as the distribution of power, all the way from where we get our sources to where the customers are at, is done under AC systems. And the electrical energy generated by our power station is transmitted at high voltages and is done so in 3 phases and 3-wire systems. Then we've got our step-down transformers that are sitting in our substations for distribution. Hence, we have to be going with the AC route for these type of systems. So in these AC systems, we've got a primary and a secondary distribution circuit. So your primary one is usually at higher voltages, and then they get stepped down by a transformer into voltages that can be delivered to us as as consumers. And there are a few differences then, therefore, between your AC as well as your DC distribution systems, and these are stated below. Mainly that in your DC distribution, your voltage drop, if you remember, was only resistive. Okay, it was always just R is equal to whatever ohms. But in AC systems, we have that voltage drop being due to a combination of your resistance, your inductance, as well as your capacitance. So it's impedance in this case. Then your current and your voltage in the different sections are obtained vectorically in your AC system, whereas they were algebraic in your DC distribution system. You could just all add them up together. Then you've got a power factor that's always have to be taken into account. And if you remember, in DCs, your power factor was assumed to be a 1, but in AC, your power factor is anything between 0.1 up until 1. Then the power factor may be referred to a supply or a receiving end voltage. So it could be on either one. Then you have to go and get whatever is the one that is not given, which is regarded as your reference phasor in that case. And the power factor may also be referred to the voltage at your load point in itself. So we're going to look at the actual examples that are in the book on AC systems. And the first one that we really have shows you a system where you've got 3 loads and you've got your supply point at 380 volts. They show you what your impedances are between all of your different nodes that you have in the system. And we're really asked to calculate the current that is within our distribution system. That means that is your AB, your BC, your AD, and your CD. And then also calculate the voltage at each load point. Now, if you look at the system, it says that this is a 2-core AC ring distribution system. It's not a 2-wire, it's a 2-core. Your number of cores are what makes up your actual wire that you have. So you need not multiply by the number of cores in order to get that impedance that you have been given. Compared to your DC, where it's a two-wire system, and the impedance, they will usually say it's per wire, so you usually multiply that by 2. But you must know that when they talk about your cores, then already your cores are making up your wires that you have. So as you saw in the previous slide, we didn't have arrows going within our system because in AC we say that our current changes periodically the direction, so it could be moving from either side on your circuit. Now, for this reason, we then have to have an open circuit section that we introduce within our circuit. So your open circuit, you must always choose it to be at the point that is closer to your end load or your furthest load. So it must be at a point closest to where your C is. Now, in the example in the textbook, they've chosen to open circuit your CD portion. You could also decide to open circuit your BC option. It doesn't have to be the one at the bottom that remains open circuited. Now, once you do the open circuit, then we're going to utilize our Thevenin's theorem in order for us to get that voltage across the open circuit place. So the first part we do now, we look at the simple ones. Because we've done the open circuit, we know that we can introduce the direction of our current flows as there are only one means going to your C point. And then it means that by default, we are forcing it so that going to our D point, we can be feeding from the bottom of where your supply point is going to be. So they start looking at your BC section, which is the one on the far side on your top section. And they say here that your line BC is going to be the same as line IC. Why is that? Because you can see that it's simply a straight line. The node doesn't have any other incoming or outgoing. So therefore, that's why the current coming in that node is going to be the same as the current coming out of that node. Then we go and look now at IAB, which is the first part of that top section. And IAB is simply going to be, if you're looking now where your node B point is, and I've drawn it nicely here on the side for you. Your IAB splits up into IB and it splits up into BC, remembering that BC is the same as IC. And check how I've nicely drawn it for you so that you can even see your BC being the same as IC. So therefore, it simply means that your IAB is going to be equal to your IB plus your IBC, which is the same as your IC. You put those two together and you get that 89.5. Then you go to your IAD, which is now at the bottom of our section here. And that simply is also going to be the same as your ID, because at that node point, there's nothing else leaving or coming. So it's simply going to be like a straight line. Your IAD is what is feeding your ID. Now that we've got those three different currents, we can go and look at our voltages on that system. So the first voltage we look at is your VAD, okay, which is at the bottom here. And that VAD was simply going to be an IAD that we've worked out multiplied by the ZAD that they give you in the system. And that gives you that voltage that you have there. Then you want to know what the VAC voltage, and what is VAC? VAC, you can see that it's going to be a combination of VAB and VBC. You already have IAB and you've already got IBC, so therefore you can substitute and be able to work out what VAC is. Then you're left with the portion that we open circuited, which is your VDC. So in this case, we say that is going to be equivalent to be our Thevenin voltage. And so therefore, that voltage is really your VAC section, subtract your VAD section. And we say here that our VAC, as we've noted above, was the same, was VAD and VBC, and at the bottom it can also be seen as VAD plus VDC. Okay, so anyway, so you've got this VAC minus the VAD, and we then can be able to put those two together and have what you have a voltage over there, that's 61.4. Then we go and work out what our Thevenin impedance is going to be. And our Thevenin impedance is simply going to be our ZAB plus our ZBC plus our ZAD. And we are able to get that. Now for us to work out what our current in our IDC, where we're utilizing the Thevenin, we must remember that it's going to be that voltage, the Thevenin voltage, which was our VDC. You divide by the ZTH and you add the ZDC, which is your open circuit at the bottom. Because as they've drawn the circuit diagram, you can simply see there you've got VTH and then you have got the VDC coming in at the bottom as well. Now, why was it not parallel in this situation? I want you to look at where your open circuit is, because that clarifies why we're not having a parallel situation like we did where the interconnector was on the DC systems. In the DC system, you had an interconnector between A and C, and then you open circuited that. That meant to go to your top section and your bottom section were in parallel. Now you've open circuit here between one of your node points. So that means that all of your other impedances are really going to be in series with one another. Then we can now be able to calculate our IDC. And as I've said, it's going to be your VThevenin over your ZTH plus your ZDC. Then that gives us what our current is on our DC side. Once we have that current, we can then go back and substitute it and work out all of the different currents looking at each node. So we start with IAD. So IAD now is not just going to be the ID that was there, but it's really going to be IDC plus ID, because you've got IAD coming into that node and leaving, you're going to have your IDC as well as your ID. Then your IBC, okay, your IBC was going towards node C. So that one is now going to be your IC, which was coming out, and then your IDC, which was also going in. So therefore, you're going to have it being there 13.1. Then you can now go back to your IAB, which is right at the start on the top hand side, and substitute this new IBC into it, and then you're going to have what those currents are going to be. So in summary, you first have to open circuit your AC system somewhere closest to your furthest load. Once you've done the open circuiting, then you can work out all of those different currents. Then find the current across your open circuit portion. Then go back and close circuit everything and substitute that current into your different equations so that you can get what the real currents were between all of your different node points. Then we go to the second part, and the second part was asking for the voltage at each node. So we go now to B. Again, B is the first one at the top. It's simply going to be our VA, which was our source. Subtract that VAB, which was the one across the first portion of your line. And then that gives us our voltage, and you can see it's going to be 364. Then your VC is the same. It's going to be your VB minus your VBC, and you get that. And your VD is going to be your VA minus your VAD, and you can be able to get what your voltage is also going to be. And that means we have actually answered now question 1 in full. So you must just know the different steps. It's a very long way to get to it. Then we go to our second example, which is EG 7.4 on your book. And here they give us the different impedances that you have: ZAB, ZBC, ZCD, and ZDA. And you can see that it's a resistance and inductance. And they say it's also a two-core system. Remember, I don't need to multiply by the 2 at all. And this network also has an interconnector. As you can see, there is a line that is drawn between your A point and your C point. So the first thing that they do, now that you've got this scenario with the interconnector in it, we look at the system and we do what we call changing your delta to a star, and you choose again where you want to change. And I must say the examples, they like choosing the bottom section, so you can also just make it easy for yourself and choose the bottom section. But I would say for practice, go and choose the top, work it out, and see if you come out with the same answers. I did the exercise last year with the group. You come out exactly with the same values at the end of the day. So anyway, looking at the converting the delta, which is ACD in this case, so it's your bottom one, to an equivalent star, you're going to have three obviously impedances that you work out. So your first one being VAN, and we already know most how to do the conversion from your delta to a star. It's a multiple of the two. You divide by the entire impedances, three of them. So therefore you can get VZAN, ZDN, as well as ZCN. And then this is how it would then be drawn. You no longer have that interconnector in. Instead, from A point you move to N, as well as from C point you move to N, and then from N you move directly to your D point. Then only you can now use your open circuit section in order for you to calculate. Now, because in this case you first started by a conversion, all right, of your delta to your star. If you chose the bottom part to do that conversion, then your Thevenin theorem must be used on the opposite part, which is going to be your top part. If you chose your top part to do the conversion, then your Thevenin theorem for open circuit is going to have to be at your bottom section. So always use the opposite one of what you used when you did the conversion of your delta to your star. So here the opening line BC, again, why line BC at the top part? Because we always open the one furthest away from the source. So therefore, if you open that, you can see that your AB is simply going to be the same as your IB, né? And then your INC, okay? So you go to your NC, you can see is that last portion at the bottom part, and that's going to simply become your IC. Then you're going to have your IAN. Now look at your IAN. Is going to be your ID, because from N it just goes straight through to D, going to what you had as your ID at the bottom. So there is no separate current that you get between N and D, because that is in series. It means that it's exactly the same and it's the only one getting in at node D. So it's going to be that ID plus my INC. Then I can work out what my IA was going to be, IAN. Now that we've got the different currents, I can then work out what my VAB is, and I can work out what my VAC is, simply being my VAN plus my VNC. Then we go and we do, what would VBC then, your open circuit portion, be? And your VBC would simply be your VAC minus my VAB. And then I get that, and I can say now my Z Thevenin is going to be similar to ZAB plus ZAN plus ZNC, because again, we don't have an impedance that's going from N to D. Then once we've now got that Z Thevenin, we can draw your circuit so that you see that there at the bottom you are going to have where you need to put in your ZBC. The textbooks put it as ZDC. I've corrected it so that you know that it's ZBC, because that's where we've done our open circuit at. So you can calculate then what your IBC is, which is simply that VBC over your Z Thevenin plus that ZBC value, and you get it. You take that IBC, you go and substitute it back into your system. So the first place you can go to is that node at the top where you've got the IAB coming in there, because you know you're going to have IB coming out as well as this IBC coming out. So you add those two together and you can get what your real IAB is going to be. Once you have that, then you can go to your bottom part of your circuit. So this is the last example that we have on AC distribution systems. Now in the example, before I even go to the questions, you can see that you've got 4 different loads here. You've got a B, C, D as well as an E load. Also, what is different about this, although there is an interconnector which is a dotted line between A and C, there's also a solid line that you see between A and D. Can you see that? Good. Now, when we go to the questions, they ask us to calculate the voltage drop that is between A and C, both with the interconnector and without the interconnector. So we're going to start without the interconnector. So remove the interconnector, and you're still going to have that line that you see between A and D. Because you've got that line that you see between A and D, and then you've got your circuit as it is, it means that between that A and D, and then E and back to A, you have got a delta circuit. So they take that delta and they convert it into an equivalent star circuit. So they go and they find the ZAN, ZEN as well as ZDN. At the top hand side, they then draw the equivalent circuit, and you've got a connection between N and E. Okay. So with this now, they then go to the using the Thevenin's theorem and open circuiting. And they've chosen the circuit C and D to open circuit. And you can do this because unlike the previous one where you only had the 3 different nodes, all right, it was better sense that you go to the opposite side in order for you to do your open circuit after you've done your delta to star conversion. But in this case, you've done your delta to star. It was not even your interconnector. And secondly, you had an additional load in here. So you are not working exactly with the same point that you've done a conversion in. In other words, you didn't touch D and C in all of your calculations when you try to do your conversion. Okay, so that's why you are able to open circuit that CD point. So then they open circuit the CD point. So now we're going to start utilizing all the different ways of calculating with that open circuit open. Just looking at the diagram before you go to the first page, you can see, looking at the top part, okay, that your IBC is obviously going to be equal to your IC, and then your IAB is going to be equal to your IB plus your IBC. Then looking at the bottom part, you see here that your ID is going to be the same as your IDN, and then your IE is going to be, your IAN is going to be the same as your IE plus your IDN. So here they are, as I have said there before, they are just doing those computations. Once that's done, then you can calculate the voltage, and the voltage is between your VAB and your VBC because they want to know our AC. So now that you've got those 2 voltages, because you know what your IAB and your IBC are, you can calculate that voltage is 118.792. Then they calculate the VAD, and the VAD is then your VAN plus your VND, and you get that voltage. Then they do the Thevenin, all right, which is across your CD point, your open circuit point. And that voltage is simply going to be our VAC, subtract our VAD. And you get a voltage that's going to be 92.746. Then you do your Z Thevenin, and your Z Thevenin is simply going to be all of those impedances added up together that are there except for the VCD one. You draw your Thevenin equivalent circuit, and you can then calculate what our IDC is going to be, because it's going to be that VDC, and then you divide by that Z Thevenin plus my ZDC. With you having now the IDC, you go back and you substitute it into your formulas. So they started at IBC, because your IBC is now going to be that IC, and then it's minus your IDC, because your IDC is going to be coming from the bottom part. So you get that 25.49. Then you do your IAB, and your IAB is simply your IBC plus IB, and you get an answer there. So therefore, now that you've got your IAB and your IBC, you can be able to calculate what your VAC is going to be. And you can see that your VAC is 63.85. So now we go to the second part of the question, where they ask for that same voltage drop, but they want to know when you have an interconnector in it. So when you have an interconnector in there, you go back and put that interconnector. You don't remove that equivalent circuit that you did already, all right? It still remains in that you've changed that delta scenario into a star scenario. And you can see now with your interconnector, like you were having at your DC section, your Z Thevenin is going to subdivide those. It makes the top part and the bottom part parallel together. All right. So therefore, the top is going to be the ZAB plus ZBC. Then the bottom is going to be your ZAN plus my ZND plus my ZDC. And I get my Thevenin equivalent circuit there. Then I can calculate what my IAC is going to be. And my IAC simply becomes that VAC divided by my ZREM or Thevenin plus my ZAC. And I get what that's going to be. And with that answer, I can then simply go and calculate what would then have been my VAC, which would have been this IAC that I got. And then I multiply it by my ZAC. Okay. And that gives me that 25.599. So you can see that without the interconnector, that voltage drop was 63.85, and with the interconnector, that same voltage drop was now 25.599. It became less with the interconnector in the system. All right. So I would advise you guys, so that you don't confuse yourself with the repetitive of VAC. I would advise you that when you do the Thevenin equivalent, okay, with this interconnector in 7.5.2, once you found the Z Thevenin, then you go to your IAC, all right, and you say that, don't say it's VAC, say it's your V Thevenin, and you divide by your Z Thevenin plus my ZAC that they give you. Then you can get that answer. And then you know you're only now going to go work out what your VAC is going to be. Otherwise, people just end up saying, I've already got VAC, so why am I doing it again? Right. And that is the end of our lesson, guys. And I want to thank you for all of your participation. We will then discuss our last assessment. In the class, we said that we are going to do a test, but it seems that it's going to be an impossible task to do. So I'm going to discuss it in a separate WhatsApp group. Thank you.